Okay, for section 1D, we're going to talk about analyzing arguments. So first of all, there are two types of arguments that we're going to discuss. The first one is called inductive, and I think of induction like the domino effect. So you're using specific premises to get to a general conclusion, and inductive reasoning is weaker than the next type of argument we're going to talk about. But just to give you an idea of an inductive argument, it would be like this. The premises are specific facts, and you're trying to use those to domino into a general conclusion. So bluebirds fly, hummingbirds fly, cardinals fly, therefore our conclusion is all birds fly. The reason it's weak is that you can easily negate the conclusion if you can come up with one counterexample. So I can all of a sudden go, well, that's not true because penguins are birds and they don't fly. And it doesn't matter how many premises are used to support this conclusion, but if I can come up with one counterexample, then I've proved the argument false. The other one is deductive. So deductive reasoning, right? Sherlock Holmes used this type of reasoning quite a bit. And in that case, you're using general premises to support a specific conclusion. It's a much stronger form of argument. But an example would be, and I want you to take this from the perspective of the logic of the argument, not even necessarily that the premises are true, because they may not be in this case, but why the logic works. So if we operate under the premise that all doctors are intelligent and that Dr. Jones is a doctor, then we can support the conclusion that Dr. Jones is therefore intelligent. So general premise, and then there's a specific premise that puts Dr. Jones within the general set of discussion, and then our conclusion is supported that Dr. Jones is intelligent. Now, it may not be true that all doctors are intelligent. We can argue about that, but in terms of the logic of the argument, this is much stronger than an inductive process. Right, so the way we evaluate inductive arguments is just through their strength. So it doesn't prove its conclusion we evaluate it on whether it's a strong argument or a weak argument. It's strong if it makes a compelling case for its conclusion. So that usually includes many premises, basically, many supporting examples. And it's weak if the conclusion is not well supported by its premises. So here's an example. A movie director tells her producer, that's the person who pays for the movie, not to worry. Her film will be a hit. As evidence, she cites the following facts. She's hired big stars for the lead roles. She has a great advertising campaign planned, and it's a sequel to her last movie. Explain why this argument is inductive and evaluate its strength. So it's inductive because there are specific premises. Namely, her examples, her anecdotes about her movie, right? She's hired big stars. So big stars, great advertising, and it's a sequel. And so, yes, it's inductive. Now, to talk about the strength of this argument, I think it's relatively weak because you can find plenty of examples of movies that had all of this, but bombed. I'm trying to think of one off the top of my head. Terminator 3. It was horrible. Yeah, any counterexample in an inductive argument renders that argument false. So if you can think of any other movies that had sequels with big stars and they advertise, oftentimes, in fact, when movies advertise too much, it's the production company trying to overcompensate for how bad the movie is. So they'll try and put out a bunch of advertising so that they can get a big opening box office, but then they know the movie won't have legs. Like, people won't go back to see it, or once people start to see that it's getting bad reviews, they'll just stop seeing it. So, in fact, lots of advertising can sometimes be a little bit of a red herring. All right. If you want to look at the solution further in depth, you can pause it in here. But it's basically what we just discussed. Okay, so in evaluating arguments, we're going to look at two criteria for a deductive argument. Its validity and its soundness. The argument is valid if its conclusion follows necessarily from its premises, regardless of the truth of the premises or the conclusion. The argument is sound if it is valid and its premises are all true. So validity really only has to do with the logic of the argument. Does not have to do with whether or not the premises are true. Once you've stated that the argument is valid, then it could be or may not be sound. So here's what I would say for something like this. This argument is valid, but not sound. If we take the premises to be true, then it's valid. If all doctors are intelligent, and we know Dr. Jones is a doctor, then it's valid to make the statement that Dr. Jones must be intelligent. My argument for its lack of soundness is the statement all doctors are intelligent. There's not, first of all, a great definition for intelligent. This is a vague, not well-defined statement. If you put any metric on intelligence, I guarantee not all doctors would satisfy that metric. So I'm saying, like, if we have to put, well, any metric other than they have, a medical degree. But my point is that intelligent is a vague term that's kind of a colloquialism, right? There are plenty of doctors who you may not agree with. There was that doctor the other week who said that the COVID vaccine was being kept silent by aliens or whatever. So I think there's an argument against intelligence there. So I think the structure is valid, but I would argue that the argument is not sound, because we can't just necessarily assume in this case that the premises are true. So here's a table that kind of gives you some important points and key distinctions about inductive versus deductive arguments. So it gives us sort of what is inductive versus deductive as an argument. Inductive, you form a conclusion by generalizing from a set of specific premises. So you're given specific anecdotes, specific examples, and you're trying to use that as a domino effect to support a general conclusion. Versus deductive, a specific conclusion is deduced from a set of more general premises. An inductive argument can be analyzed only in terms of strength, and a deductive argument we analyze based on two conditions: validity, which is the structure of the argument, and soundness, which is can we accept the premises to be true. An inductive argument can't prove its conclusion too. At best, you've given a bunch of examples, and so you've put up a strong argument, right? So a strong inductive argument might be like, alien life forms have never visited Earth, right? We don't have any evidence, or we have very little valid evidence of that happening. Now, I can't prove that, because you would have to literally go throughout all time that Earth existed and at all points on the Earth's surface and make sure that no alien had been there. And that's that is impossible. But you can present a strong case. And then validity concerns only logical structure. So a deductive argument can be valid even if its conclusion is blatantly false, as long as its structure holds up. All right, so we can use Venn diagrams to test validity. And the way you do it is you draw a Venn diagram that represents all the information contained in the premises. And if the Venn diagram confirms the conclusion, the argument is valid. Otherwise, it is not. So let's go over how to do that in an example. So here is a propositional argument. All fish live in water. Whales are not fish. Therefore, whales do not live in water. And so the way we would do this is the first statement, we are going to use the first premise to make our Venn diagram. The second premise we're going to use to place an X on our Venn diagram. And then we're going to see if where we place that X supports the conclusion. If it does, the argument is valid. If it doesn't, the argument is not valid. So all fish live in water. We can rethink that as a conditional statement, as an if-then statement. So I can describe that as if something is a fish, then it lives in water. Oh, excuse me. And that'll help me to look at the two sets, right? So I'm looking at the set of fish and then looking at a set of things that live in water. And this is a subset relationship. So you can see here, we would put fish inside of the set of things that live in water. Now we're going to use our second premise to place our X. So our X is going to go based, like I said, based on our second premise. So whales are not fish. So we know for a fact we have to place that X outside of the fish set. But that premise says nothing about whether or not whales are still things that live in water. I know we know whales live in water, but we're placing our X specifically based on that second premise. So whales may or may not live in water based on that second premise. It's not mentioned. So to indicate that, we place it directly on the border of the set of things that live in water and the set outside that, the universe that we're thinking of. So that's indicative of it could be in either. It doesn't have to be in one or the other. And then we look at our conclusion. Whales do not live in the water. And we want to think, does this placement of our X support that conclusion? Well, if whales don't live in water, we would expect the X to be fully outside of the set of things that live in water. But because we had to place it on the border, the argument didn't state whether or not they live in the water. They may live in water or not based on this. The X is not fully placed outside of that set. So based on where we place this X, we're going to say that this argument is invalid. So its logical structure does not hold up. Because of that, it cannot be sound if it's not valid. So just invalid. All right, I'm going to give you 4 basic forms of conditional deductive arguments. And if they have these structures, they are valid or invalid. They have kind of fancy names, so you might want to pause this and take a minute to copy down this table. But first one is affirming the hypothesis, and that has this form. If P, then Q. That's the first premise. The second premise is P is true, and then the conclusion is then Q is true, and that's a valid form of argument. The second one is called affirming the conclusion, or sometimes referred to as consequent. If P, then Q, and then the second premise is Q is true, and then they conclude that P is true. That's an invalid form of argument. It's not have a correct logical structure. Third one, denying the hypothesis or antecedent. If P, then Q. Then the second premise is P is not true, and then they conclude that Q must not be true. That's also invalid. And the last one, denying the conclusion, which is consequent. If P, then Q. And the second premise is that Q is not true, so the conclusion is that P is not true, and that's valid. So you'll notice that a couple of these have the same names. And this is kind of an analog of the relationship between conditionals and their different forms, right? So inverse, converse, contrapositive, and how a couple of those are logically equivalent to each other. So a couple of these argument types are also logically equivalent to each other. All right. So let's try one together here. If a person lives in Chicago, then the person likes windy days. Carlos lives in Chicago. Carlos likes windy days. So first thing I'm going to do is build a Venn diagram out of this, right? So we're going to go, what are the sets of people that we were talking about? It's the set of people that live in Chicago and the people that like windy days. And the way that they've set up this conditional is a subset relationship. If they live in Chicago, then they like windy days. So let's see if we can construct a Venn diagram for this. Oops. So create my universe here. So if a person lives in Chicago, then the person likes windy days. So that means that living in Chicago is a subset of liking windy days. So I'll put the outermost circle is likes windy days, and the innermost circle is lives in Chicago. And then we're going to place our X based off the second premise. Carlos lives in Chicago. So I can place Carlos and X straight inside that set of people who live in Chicago. And the conclusion is Carlos likes windy days. Well, as you can see, he definitely also falls within that likes windy days subset. So I would call this a valid argument. Now, it's only sound if we can assume the premises are true. So this is where you like jump into the real world. You're out of the world of just strict logic and you're going, all right, is that true? Do people who live in Chicago have to like windy days? Not necessarily. I'm from Chicago. I hate the wind. Not sound. It's unreasonable to assume everybody in Chicago likes windy days. Also, not why it's called the Windy City. It's called the Windy City because of the politicians that were there in like the 1930s were said to be windbags. So it was more of a pejorative term, not anything to do with the actual wind there. All right. And so let's just go back and talk about which one this was. So if P, then Q, P is true. So this is going to be affirming the hypothesis, right? If live in Chicago, then likes windy days, lives in Chicago. So we're affirming the hypothesis of that conditional statement. Whoops. So let's do a second one. If an employee is regularly late, then the employee should be fired. Sharon was fired, therefore Sharon was regularly late. So I'm just going to look at this pre-made Venn diagram over here. So we're looking at two sets, the set of people that are regularly late and the set of people that are fired. Regularly late is a subset of fired in that case. And it says Sharon was fired. So we know Sharon exists within the fired circle, but it says nothing about whether she was regularly late. So she may or may not have been. To indicate that, we're going to put the X representing Sharon on the border, meaning it could be just in the fired or in the regularly late as well. And then the conclusion was that Sharon was regularly late. Again, we can't assume that. She's on the border there between the sets. So this is an invalid argument. Right? And this was a case of affirming the conclusion. The conclusion was the person is fired. and we're affirming that she was fired, but you can't conclude from that that the hypothesis was also true. That's not a valid form of argument. All right, let's try another one. Use a Venn diagram to test the validity. If you like the book, you'll love the movie. Okay, so let's build the Venn diagram based off of that. I'll put it way up here. So we have two sets. So if you liked the book, you'll love the movie. So that means liked the book is the subset. And love the movie is the superset. Okay. Second premise, you did not like the book. All right, so you're definitely not in the red circle. But that second premise doesn't tell us anything about whether you're in the blue circle or outside of it, so I have to put the X representing you on the border there. And the conclusion is that you will not love the movie. Not necessarily true. You may still love the movie, you may not. I'm going to call this an invalid form of argument, and let's analyze which type it was. So, you did not like the book argues against the hypothesis. So going back, it's arguing against the hypothesis, so it's denying the hypothesis, which is an invalid form of argument. So we are denying the hypothesis. All right, but you can guess what the next example is going to be. All right, so a narcotic is habit forming. Let's turn that into an if-then statement so that we can make an easy Venn diagram out of it. So if something is a narcotic, then it's habit forming. All right, we can build our Venn diagram based off that. So here's my universe. So if something is a narcotic, then it's habit forming. So I'll do things that are habit forming. And our subset within that are narcotics. All right, now we're ready to place our X based on the second one. Aspirin is not habit forming. So it's outside of the habit forming circle completely. Whoops. So it's all the way out there. Therefore, aspirin is not a narcotic. I would agree. You can see where our X is. It's definitely not within the narcotic circle. So this is valid. All right, so now if it's valid, we need to decide if it's sound. So premise, narcotic is habit forming. That's scientifically and empirically true. Aspirin is not habit forming. Also, lots of evidence to support that. So I think it makes sense that we can assume both premises are true, which means since it's already valid, we can say it's valid and sound. Okay, so now let's categorize this. The second premise, aspirin is not habit forming. That denies the conclusion. So it says the opposite thing of the conclusion of our first premise. So this is called denying the conclusion, right? Which is a valid form of argument. All right. Whoops, okay. So just one more thing, you can have sometimes a chain of conditionals. So it's just a longer argument, but the logic of the argument works the same way. So you can have if P then Q, if Q then R, and then you can conclude if P then R. It works almost like the transitive property, right? If A equals B and B equals C, then A equals C. So it works similar to that. You can kind of link these things together is the idea. So if elected to the school board, Maria Lopez will force the school district to raise academic standards, which will benefit my children's education. Therefore, my children will benefit if Maria Lopez is elected. So we can kind of break this out as a chain of conditionals. So the first one we would do, right, is if Maria Lopez is elected to the school board, then the school district will raise academic standards. And then the next one will be, if the school district raises academic standards, then my children will benefit. And then we can conclude, if Maria Lopez is elected to the school board, then my children will benefit. And because it forms that logical chain, kind of almost using that transitive property, right? P is Maria is elected to Q is elected. Q is the district will raise academic standards, and R is my children will benefit. So therefore, the argument is valid. So mathematics relies on the idea of proof. A mathematical proof is a deductive argument that demonstrates the truth of a certain claim or theorem, and a theorem is considered proven if it's supported by a valid and sound proof. So mathematical proofs use deduction. Theorems are often discovered by induction, meaning a mathematician will start seeing a series of patterns. They'll be working on problems and they're like, oh, this same thing tends to happen over and over again. Maybe this is the conclusion to that. So that's how they kind of stumble upon the idea. Then they try to prove it using deduction. There is something called mathematical induction or strong induction that can be used, but it's beyond the scope of this class, and it can be used as proof. So here's an example that might have led somebody to discover the commutative property, so which is for all numbers A and B, A times B equals B times A. And so you could test some cases that have different characteristics in the numbers. Like the first case, these are just whole numbers. 7 times 6 equals 6 times 7. Well, it does. In the second case, we're using both negative and positive, and we're also using decimals. And it works out. And then you might use fractions, and it works out. So now you maybe have some evidence to start looking for a deductive proof. All right, last thing for you guys. This is your student example. I'd like you to create a Venn diagram and analyze the argument. So you're either going to tell me about its validity and soundness, and then classify it as a conditional argument. So go back to that table and classify it as affirming the premise or affirming the conclusion or denying the premise or denying the conclusion. All right, good luck. We'll talk about it in our next class.